In this lesson, you're going to learn all about 3D rotation. Now, rotation in 2 dimensions is very simple. It's just one single angle. Rotation in 3 dimensions can be a little bit tricky. This is one of the more difficult concepts in 3D graphics, and even I still run into some rotation problems that are difficult to solve. Fortunately, you don't have to be a complete master of 3D rotation in order to use it, but I want to make sure you understand how it works and some of the issues that you can potentially run into. Now, the easiest way to store 3D rotations is something called Euler angles, and these are easy to understand for humans. It's just a rotation on, you store a rotation for all of the 3 axes. So we have a rotation for x, y, and z going around each axis. And these are commonly referred to as pitch around the x-axis, yaw around the y-axis, and roll around the z-axis. Now, we saw the left-handed rule for coordinate systems, and we also use a left-handed rule for rotation. If you want to know which direction a Euler rotation goes around one of the axes, you just hold your hand like this, you point your thumb in the direction of the axis, in the positive direction, and your fingers will curl in the direction of the rotation. So if this is the positive y-axis, then this gives you the direction of rotation around the y-axis. So if you increase the rotation, then it's going to turn this way. And that works for all 3 axes.
LEDWorks uses a left-handed coordinate system, which means if you take your left hand and hold it up like this, then this is the x-axis, this is the y-axis, and this finger will point in the direction of the z-axis. Now we also use the left-handed rule for rotation. So if you take your hand and go like this and point it in one of these directions, so x, y, z, if we point our thumb in the direction of the x-axis, then our fingers will curl in the direction of positive rotation. If we point our thumb in the direction of the y-axis, our fingers will curl in the positive direction for rotation on that axis. And the same thing for the z. It'll be like this. Let me show you with an object. So positive rotation is this way on the x-axis. On the y-axis, it's going to be this way. And on the z-axis, positive rotation, let's see, it'll go like that. So positive x, negative x, positive y, negative y, and then positive z, negative z. Again, if you ever get confused, just point your thumb in the direction of the axis. That's the positive rotation for x, positive rotation for y, and for z, positive rotation is this way.
Order of rotation is an important concept because these rotations in a Euler angle are applied in a specific order. If you change the order, then you'll get a different result. So I'm going to show you that. We'll just drag this spaceship into the editor. And we'll select that, go to the properties. And under transform, we'll start applying some rotations to this. So I'm going to rotate it like this. That's yaw because that's around the y-axis. And this is pitch. So you can see I'm increasing the pitch. And the order of rotation here, the order these angles are applied, is first yaw, so first it will rotate around like that, and then pitch will be applied so that it rotates around its current x-axis. So it goes yaw first, and then pitch, and then finally roll is applied last. And this order of rotation, it gives us good results, because if you just have pitch and yaw, for example, this gives us results that we usually expect. Okay, now there's an issue called gimbal lock, and let's see, I want to show you. Let's get the negative 85. Okay, so as we get to very close to 90 degrees, that's yaw, and this is roll. So when we're at positive or negative 90 degrees, yaw and roll are actually rotating around the same axis. And this can cause some problems. I've got a code example that shows this. Okay, so I'm going to open the script editor, and I have, this is main.lua, and I'm just going to paste the example that I copied from the written tutorial. And what this does is each frame, it gets the current rotation, and get rotation returns the Euler rotation. So this is a vec3, and x, y, and z mean pitch, yaw, and roll rotation. And then I'm going to use the right and left keys and the WASD keys to change the values of pitch, yaw, and roll in that rotation, and then I'm going to apply it back to the model. Okay, so I'm hitting the W key to tilt the ship up. And when we get up to the top, you can see it's getting confused. The ship is like, it's kind of bouncing back and forth. And same thing when we go down here. Okay, so what's going on here? This is, if you ever see this happening in your game, this is gimbal lock. The problem here is that because when you approach 90 degrees pitch, yaw and roll become the same, they are rotating around the same axis. That means that although each Euler rotation accurately describes one orientation, if you start with an orientation and convert it into Euler angles, there are multiple solutions to that. And what I'm doing right here is I'm calling ship turn 1 degree on the x-axis, and then I'm calling it ship turn again negative 1 degree. So I'm moving it, I'm pitching it forward 1 degree and then pitching it back. And what that does is it resets the internal Euler rotation stored for this entity. And when it does that, it doesn't know what the correct Euler is supposed to be because there are multiple solutions. So although Euler angles are human intuitive, they're easy for us to understand, they're also ambiguous. They're not a perfect representation of rotation.
Euler angles are an intuitive way to describe rotation with 3 angles, one for each axis. You have pitch, which is on the x-axis, yaw on the y-axis, and then z on the object's z-axis. And these are applied in the order of yaw first. So we'll rotate it like that, and then we apply pitch, and it'll go like that. And then you roll will make the object roll around its z-axis like that. Now the problem here is that as we approach 90 degrees pitch, yaw is like that and roll is like this. But as we get closer and closer to 90 degrees, those become the same axis. So now we have this rotation can be described with many different Euler angles. There isn't just one solution, and that is the problem of gimbal lock. I'll show you one more time. We'll start here, and yaw is like this. And as we pitch up, yaw is like this, and roll is doing this. But if we go higher, then eventually those become the same axis that it's rotating around. And that is the problem of gimbal lock.
So to solve that, we have another type of rotation called a quaternion. And a quaternion is a four-dimensional structure. It has values for x, y, z, and w, and it uses that to define a rotation with no ambiguity. Every quaternion can be describes very precisely a rotation, and there's no guessing like what the right value is. Now, quaternions are not human friendly to understand. I don't understand what the numbers mean. There are entire books about visualizing quaternions. You can read that if you want to. Maybe someday I will. But you don't need to understand what the numbers mean. You just need to understand that a quaternion is a perfect representation of a rotation. So let's copy this example. And I want to show you how this uses quaternions to fix the problem of gimbal lock. Okay, so internally the entity stores a quaternion for the rotation. It stores both the Euler and the quaternion. And this turn function here, this will actually rely on the internally stored quaternion. So instead of adding numbers to the Euler angle, I'm now just calling turn 1 degree each frame. And let's see what effect that has. So let's pitch the ship up. And now the rotation just works perfectly. So the takeaway here, the thing to remember is if you're making a first-person shooter and you're just storing a pitch and a yaw for the player, then this might not be a problem. If you're making a game like Descent where you have a ship that can rotate in every direction, like this, then you're definitely going to want to use quaternion rotation because that's going to be able to handle every type of rotation, even tricky ones where the pitch approaches 90 degrees. So it's kind of a weird concept, but it's just something to keep in mind that it's always better to use the turn method because this will use the internally stored quaternion rotation. Okay, now I want to show you something special we can do with quaternions called spherical linear interpolation. So let's start with this example. We'll copy that. And then paste it. And let's just run it and see what happens. Okay, now we have this ship that's rotated a certain way. And when I press the space key, it's going to move to another rotation. So this is actually using the mix angle function that we saw before on each axis of Euler rotation. And you can see it is smoothly interpolating the rotation, but it seems kind of weird, doesn't it? It doesn't look like it's using the most optimal path to get there. It seems like it's got a lot of extra motion. So this is what we're doing. We're calling ship set rotation mix angle ship rotation dot x. That's the x component of the ship's current rotation. And then our target rotation. The target rotation is just these two rotations. And then when we hit the space key, we're switching back and forth. So we use this mix angle function on each axis. And so they're operating independently. And the results don't look quite right. It seems like it's kind of taking a long route to get there. The solution is to use spherical linear interpolation. So if we just copy and paste this little snippet, and we can comment this out, and then we're going to paste in our new code. Okay, let's take a look at what this does. Q current equals ship get quaternion. Not get rotation, get quaternion. This returns the internally stored quaternion rotation. And then we're going to create another quaternion called Q target. And to do this, we're just converting this target Euler rotation into a quat. This is one of the quaternion constructors. So we can just supply a Euler angle and it will turn it into a quaternion. And then we're going to say ship set rotation Q current slurp, which means spherical linear interpolation. And then the target value is our Q target quaternion. And then we're going to use 0.05 for the blend value. So this is sort of like mix angle, but it works in 3D between two quaternion rotations. And we'll look at the difference that makes. Now you can see it's taking a much more optimal route. It's not waving around in different directions unnecessarily. It's just taking the shortest route between those two rotations. So if you want to rotate, if you want to interpolate between two rotations, and you want to support 3 axes of rotation, then spherical linear interpolation is the right way to do that. If we were just rotating it on one axis, I mean, if it was just like a car, or if it was just rotating on flat land and it only turned around its y-axis, then it would be okay for us to use mix angle. But if we use quaternion with the slurp method, then that will use spherical linear interpolation to smoothly interpolate between any two rotations, no matter what they are. And that will always use the shortest distance between those two rotations, and it will just always work without any problems with gimbal lock, without a lot of unnecessary motion. Spherical linear interpolation is the way to handle that.